Welcome to a new deep dive. Today we're journeying inward, right towards the very heart of our home galaxy, the Milky Way.
Mm-hmm.
It's a familiar name, sure, but when you look closer, parts of that central region are really quite shrouded in mystery.
That's absolutely right. We know it's this beautiful spiral galaxy, but hidden inside that dense core is a structure that's, well, incredibly important for its whole story.
But also incredibly difficult for us to actually see clearly.
Exactly. From our vantage point out here in the disk, looking inwards is tough.
And that structure we're talking about is the central bar. You can sort of picture it like a giant elongated box of stars, right smack in the middle.
Yeah, a really crucial feature, but one that's been, challenging astronomers for ages.
The big problem, like you said, is we're stuck inside the galactic disk.
Hmm.
So looking towards the center means trying to peer through just loads and loads of interstellar dust.
And our view is edge on.
Right, which
Yeah.
makes it like trying to understand a whole book just by looking at its spine. It's really limiting.
Yeah, it's a real puzzle trying to figure out its precise shape from here or, how big it actually is, even how fast it's spinning.
So our mission today in this deep dive is to try and peel back some of those dusty layers
Yeah.
using the sources you brought together.
Right.
We're going to unpack what these studies tell us about this hidden bar.
Hmm.
What is it fundamentally? Where might it have come from? How does it throw its weight around the galaxy?
And crucially, what's the really revolutionary new data, especially from the Gaia mission, finally letting us see?
Yeah, that sounds fascinating.
We've pulled insights from, well, a whole stack of articles and research papers. It covers everything from the foundational ideas about how galaxies work, dynamically speaking, right up to the latest findings combining data from missions like Gaia with other big sky surveys like APOG.
Okay, great. Let's dive in. Maybe start at the beginning. What is a galactic bar, fundamentally?
Okay. So at its heart, it's basically a prominent, somewhat rectangular, maybe boxy-looking collection of stars. And it's concentrated right in the central region of, well, many spiral galaxies, not just ours.
Okay, so are they common features then? Or is the Milky Way kind of unusual in having one?
Oh, they're super common. Studies show that somewhere between, say, half and maybe two-thirds of all spiral galaxies have bars.
Wow, that many.
Yeah.
Yeah.
And if you look at all galaxies, barred spirals make up maybe a quarter to a third of the total population.
Okay.
And they come in different strengths, too. Some are really obvious, very pronounced. Others are a bit more subtle.
Right.
You often see them much more clearly if you look in infrared light.
Because the infrared cuts through the dust better.
Exactly. That dust blocks visible light, but infrared light can penetrate it much more easily.
Interesting. So what makes a galaxy end up at the bar? Is there like a pattern to it?
Well, research suggests their presence seems to depend on a few things, like the galaxy's environment. Is it isolated or in a cluster? Also, its total mass and how much gas it contains.
Okay.
And we also see that the fraction of galaxies with bars changes over cosmic time. Meaning there seem to have been fewer barred galaxies way back in the early universe than there are today. So they form and evolve.
Gotcha. So they're common, they're important drivers of galaxy evolution, but studying ours is uniquely tricky.
Right. Because of where we sit and all that dust obscuration.
So how did astronomers even start to figure out the Milky Way's bar without getting a clear picture?
Well, they had to get pretty creative, Instead of just seeing the bar directly, they started looking for its signature.
Its influence.
Exactly. Its gravitational influence on things they could observe more easily. So this involved looking at the movement, the kinematics of gas in the inner galaxy, both the neutral hydrogen, Hi, and the molecular hydrogen, H2.
And how does gas movement help?
Gas tends to flow along gravitational contours, so its motion can actually reveal the underlying shape of the potential that's created by the bar, even if you can't see the bar stars themselves clearly.
Ah, okay. Clever.
Yeah. And they also spent a lot of time counting specific types of stars, like red clump giants.
Why them specifically?
Because they're really great standard candles. They have a predictable intrinsic brightness, which means you can measure their distances quite accurately.
Right.
So by mapping out where these red clump stars are, you can map density distributions. And those maps started hinting at this elongated bar-like shape in the center.
Okay. Any other methods?
Yeah, even gravitational microlensing events were used.
Those brief brightenings when something passes in front of a star.
Yep. The pattern and frequency of those events depend on the distribution of mass along the line of sight. So the extra mass concentrated in the bar influences the microlensing statistics towards the galactic center.
So it's a bit like feeling around in the dark for its shape using all these different clues.
Pretty much.
Why is understanding this bar, our bar, so important for the galaxy's whole story?
Well, because bars aren't just static ornaments sitting there, they're really dynamic engines. They drive significant processes within a galaxy.
Like what?
They redistribute angular momentum, they essentially stir up the stellar disk, and they interact gravitationally with the surrounding dark matter halo.
Okay.
And maybe most crucially, they're very efficient at funneling gas. They can sweep up gas from the outer parts of the disk and channel it down into the galactic center.
And what happens to the gas then?
That influx of gas can then fuel bursts of intense star formation activity right near the center. Or it can even feed the supermassive black hole that we know lurks at the very nucleus of the Milky Way.
Ah, so it's not just a shape. It's like a vital piece of the galactic plumbing system, driving stuff happening in the middle.
You could definitely think of it that way, yeah.
Which brings us to how these things, bars, and maybe even spiral arms too, actually form and keep their shape.
Mm-hmm.
Sources mention they arise as inevitable consequences of stellar orbits.
Can you unpack that a bit?
Yeah, that's a key concept. It means the bar isn't like a solid structure, like a bone in your body.
Right. It's actually a pattern. It's formed by vast numbers of individual stars, each on its own orbit, but with those orbits aligned in a particular coherent way.
Okay.
The foundational ideas for this go way back to some of the early pioneers in galactic dynamics, people like Lindblad, Kalnash, two more. They figured out how these large-scale patterns can emerge just from the collective motion of stars in a disk galaxy.
And stellar orbits in a galaxy. They aren't simple ellipses like planets going around the sun, are they?
No, not at all.
Because the galaxy's mass is all spread out, not just concentrated right in the center.
Exactly. The gravitational pull is much more complex. A typical star's path in a galactic disk looks more like a rosette pattern. It orbits the center, sure, but it also kind of bobs in and out radially as it goes around.
A rosette with a wobble.
Yeah, basically.
And-
And that radial bobbing, that wobble, happens at a specific rate called the epicycle frequency.
Okay, so you've got these complicated rosette orbits, each with its own radial wobble or epicycle frequency.
Yeah.
How do you get a stable bar or a spiral arm pattern out of that chaos?
Ah, well, this sounds like where those orbital resonances you mentioned earlier come into play.
Yes, resonances are absolutely key here. Think of pushing a kid on a swing, right? You push it just the right time.
Exactly. You push at just the right frequency and you build up a really large amplitude swing. In a galaxy, resonances happen when a star's own orbital frequencies, like its main orbital period around the center, or its epicycle frequency, that wobble rate match up in some way with the rotation speed of a gravitational pattern, like the bar or a spiral arm.
Okay? And there are specific types of resonances.
Yep, there are a few key ones. There's the corrotation resonance. That's pretty intuitive. It's the radius where a star orbits the galactic center at the same angular speed as the bar pattern itself rotates.
Okay, they go around together.
Right. Then, closer into the center, you have the inner Lindblad resonance, or ILR. This happens where a star's radial bobbing frequency, the epicycle frequency, syncs up in a specific ratio with how often it encounters the bar's gravitational pull as it orbits. Basically, the star overtakes the pattern peak at just the right frequency.
And the outer Lindblad resonance.
That's further out. It's kind of the opposite situation. The bar pattern overtakes a slower moving star, and again, their relative frequencies sync up in a resonant way.
Okay, I think I follow. So how do these specific resonant orbits actually build and, like, hold together a bar structure?
Well, research and simulations show that within the region defined by the inner Lindblad resonance, certain types of orbits tend to get trapped. Specifically, elongated orbits that align themselves with the bar's main axis.
Ah, they line up.
Exactly. As more and more stars settle into these aligned elongated orbits, they naturally enhance the density of stars along that axis. This reinforces the bar shape. It's kind of a self-sustaining dynamical process.
I'm guessing this is still a bit of a simplified picture.
Oh, for sure. There are definitely layers of complexity. You have interactions with spiral arms, the influence of the central bulge, the dark matter halo. It all gets tangled together.
Right.
Our understanding really took a big leap forward, though, with the advent of powerful numerical simulations.
Computers modeling galaxies.
Yep. Early simulations, for instance, by researchers like Francois Combs and others, revealed something really quite surprising back then.
What was that?
They found that if you simulate just a thin disk of stars without putting it inside a massive dark matter halo,
Hmm.
that disk is often dynamically unstable. It very quickly collapses or buckles into forming a really strong bar. Sometimes it even puffs up vertically.
Wait, so the fact that not all disk galaxies have these super strong bars was actually early evidence for dark matter halos.
That's what some of those early simulation results strongly suggested, yeah. The idea was that the gravity of the dark matter halo provides this essential stabilizing influence on the disk, preventing this runaway bar formation from happening in every single
Right.
galaxy.
Okay, that's clever.
Yeah.
And what about the latest really huge cosmological simulations? Do they confirm this general picture?
They do, largely. These state-of-the-art simulations like Illustris TNG or New Horizon EGLE, they follow galaxy formation within a cosmological context. And yes, they confirm that bars form naturally in evolving disk galaxies, and they can persist for billions of years.
But did they all agree on how common bars should be?
Well, interestingly, they predict a pretty wide range in the fraction of galaxies that end up barred. It can vary quite a bit between different simulation projects, maybe from 5% up to 55% or so.
So there's still details to figure out there.
Definitely. It tells us how complex the interplay is between star formation, gas physics, mergers, halo properties. All that stuff affects bar formation.
Right.
But it's also really exciting that with the James Webb Space Telescope, we're now actually spotting bars that were already formed in galaxies much, much earlier in cosmic history, even back at redshifts greater than 2.
So bars have been around for a long time.
Seems like it.
Okay, so the general principles are kind of understood, but actually figuring out the specific details for our own Milky Way's bar, that's been the really tough nut to crack.
It really has, because again, we're looking right through the galactic center, this incredibly crowded region. It's just incredibly challenging to disentangle which stars belong to the bar versus, say, the classical bulge, or the inner part of the disk, or the interstellar halo, or maybe even other thinner components.
It's like trying to pick out one specific conversation in a really packed, noisy room.
That's a pretty good analogy, yeah.
So, despite those challenges, did scientists manage to estimate any parameters for our bar, before all the latest Gaia data came along?
Oh, yes. Using various methods over the years, star counts, gas kinematics, microlensing like we talked about, researchers did piece together a kind of working picture.
What did that picture look like?
Well, the estimates generally suggested the bar's stellar mass was somewhere around maybe 7 billion times the mass of our sun, plus or minus a billion.
Okay.
Its long axis was thought to be tilted maybe 25 to 30 degrees, roughly, away from the line connecting us directly to the galactic center.
And how long was it?
The half length, so from the center out to one end, was typically estimated at around 5,000 light years, or 5 kiloparsecs, maybe plus or minus 200 light years.
And thick.
Actually quite thin compared to its length. The scale height was estimated around 180 parsecs, so maybe 600 light years thick, roughly, and maybe 6 or 7 billion years old.
Okay, so a decent sketch. What about its speed? How fast is that pattern actually rotating?
That was one of the hardest things to nail down, and the estimates really varied quite a lot.
Right.
Early estimates for the pattern speed, often derived by trying to match simulations to observations, hovered somewhere around, say, 40 to 50 kilometers per second per kiloparsec.
Kilometers per second per kiloparsec. That's a weird unit.
It is a bit. It combines speed and distance. It tells you how much faster something is moving for every kiloparsec you go further out along the bar, essentially describing the angular speed.
Okay, and that speed determines this corrotation radius you mentioned.
Exactly. The pattern speed sets where corrotation happens. Based on those early speed estimates, the corrotation radius was thought to be somewhere between maybe 4,500 and 7,000 light years from the center. So the physical bar itself is thought to be located inside that radius.
Okay, so we have these estimates, but with pretty big error bars, especially on the speed.
Yep, lots of uncertainty there.
Now, you mentioned the bar is physically confined within that corrotation radius, but its influence can extend further out. How does that work? How does the structure that maybe ends 5,000 light years away affect stars much further out, like even near us?
Yeah, that's one of the key dynamical effects, and it's really important. Even though the main density enhancement of the bar, the visible part, stops around corrotation, its gravitational potential isn't perfectly smooth, and it doesn't just abruptly end.
Okay.
Those resonances, we talked about the Lindblad resonances, corrotation itself, they can dynamically influence the orbits of stars at much larger distances. Well, as the bar rotates, these resonant effects essentially stir things up. They perturb the orbits of stars throughout the disk, leaving these detectable patterns or signatures in their velocities.
Signatures we could potentially see.
Exactly. Even out here, near the sun, about 25,000 light years, or 8 kiloparsecs from the center.
And this distant stirring,
Hmm.
this connects directly to the specific features we actually observe in the stars near us.
It does, very strongly. It's linked to certain groups of stars that have peculiar velocities compared to their neighbors. These are often called streams or moving groups when you look at them in velocity space.
Okay.
A prime example, maybe the most famous one, is the Hercules stream.
Hercules. I've heard of that.
Yeah, it's a prominent anomaly, a clump of stars moving differently than expected right here in the solar neighborhood.
And the bar causes that.
Well, even with earlier data, like from the ESA's Hipparcos mission back in the 90s.
Right, the precursor to Gaia in some ways.
Exactly. Researchers combine those local stellar velocities from Hipparcos with dynamical simulations. And they realized that if the Milky Way had a bar rotating at a certain speed, maybe around 50-something Coulomb SKPC was one early estimate, it could naturally create features like the Hercules stream through its outer Lindblad resonance.
So even back then, there was evidence that the bar's dynamical reach extended all the way out to our neighborhood.
The hints were definitely there. It showed the bar wasn't just some isolated central feature.
Okay, so we had these hints, these indirect measurements, the simulation results, but then Gaia comes along, and this is where things really changed, right?
Oh, absolutely revolutionary, game changer. Gaia has measured the positions, distances, and crucially, the precise motions across the sky, the proper motions for, well, billions of stars.
Yeah.
Billions! With unprecedented accuracy.
Wow.
And when you combine Gaia's proper motions with radial velocities, that's how fast stars are moving towards or away from us, which you get from ground-based spectroscopic surveys like APOG.
APG, right, mapping the chemistry in motion.
Yeah. When you put Gaia and APOG together, you get this truly dynamic 3D view of stellar motion throughout a huge volume of the inner galaxy. It's just an incredible data set.
So what kind of details did this combined data start to reveal about the bar itself?
Well, studies using this data were able to create these incredibly detailed maps of stellar velocities across vast regions of the inner Milky Way. And these maps show these distinctive dynamical signatures. Things like a specific pattern in the radial velocity field, known as a quadrupole signature, or a noticeable minimum in the average rotation velocity right along the bar's axis.
And these are signs of a bar.
These are exactly the kinds of patterns you'd expect to see from stars whose orbits are being strongly shaped and aligned by a rotating bar potential. These patterns just popped out beautifully in the Gaia data releases.
So the evidence became much more direct.
Much more direct, much clearer.
And did this new, incredibly precise data allow scientists to finally nail down those fuzzy bar parameters better, like the speed and the length?
Yes, big progress there. Using the Gaia data, often combined with APG, and feeding that into advanced N-body simulations, those computer models of the galaxy. Recent studies have significantly refined the estimates for the bar's pattern speed. They've really narrowed it down now to around 40 kilometers per second per kiloparsec. Give or take maybe one or two.
Much tighter than the old estimates.
Much tighter, yeah, with much smaller uncertainties than before. And these studies also used the data to infer when the bar likely formed.
And when was that?
The current thinking points to maybe about 8 billion years ago.
Okay. How do they figure that out?
Well, the idea connects it to the evolution of the gas disk. The thinking is the bar probably formed when the gas disk in the early Milky Way became less turbulent, less chaotic.
Right.
That allowed a really thin, dynamically cold stellar disk to settle down. And such a thin disk is actually prone to bar instability. So once it formed, boom, the bar likely developed quite quickly.
Interesting. Okay, so the pattern speed is clear, the formation time is estimated. What about the length? Was that finally sorted out?
The precise length is still debated a little bit. The estimates from different studies, sometimes using slightly different methods or star samples, still range a bit, maybe from about 3,500 light years up to the older value of 5,000 light years for the half length.
So still some wiggle room there.
Still some wiggle room. For example, some recent work using a large sample of Gaia apogee stars to carefully model individual stellar orbits derived a sort of dynamical length for the region really dominated by bar orbits of about 3,400 to 3,900 light years.
Okay, maybe slightly shorter than thought before.
Potentially. And that same study found a pattern speed very close to 39 kilometers per second per kiloparsec. So the numbers are definitely converging, but maybe the exact edge isn't perfectly sharp.
Right. Makes sense. And is Gaia also helping scientists explore the bar's influence even further out beyond the solar neighborhood?
Definitely. People are using Gaia data to look at stars way out in the outer disk now. And they're finding velocity patterns like wiggles or correlations in certain populations, things like young Cepheid variable stars or older red giant stars.
And these could be linked to the bar.
Yeah, the idea is these features might be the signatures of the bar's resonances, like the outer Lindblad resonance or even higher order ones, stirring things up way out there. It suggests the bar's dynamical effects could extend surprisingly far across the galactic disk.
Wow. Okay, now this next part. This is where sources say it gets truly fascinating. There was a remarkable result from Gaia data that apparently provides compelling, though maybe circumstantial, evidence for the dark matter halo itself. How on earth does the bar connect to dark matter?
Right, this was genuinely one of the biggest aha moments that came out of the early Gaia data releases, particularly Gaia DR2. It really highlights the incredible accuracy and fidelity of the data.
Okay, I'm intrigued. What was the finding?
Several studies, notably some work led by Chiba and colleagues, took a really close look at the precise motions of stars right here in our local solar neighborhood. And their detailed analysis revealed that these local stellar kinematics, they imply something pretty profound about the bar, thousands of light years away in the galactic center.
Which is?
It appears the bar is decelerating. It's actually slowing down its rotation over cosmic time.
The bar is slowing down.
Wow.
What would cause a massive structure of billions of stars like that to slow down?
Well, the most consistent and really the most powerful explanation we have for that is dynamical friction.
Dynamical friction. Sounds like drag.
It is, essentially. It's a gravitational drag force.
Oh.
It's caused by the bar's interaction with the massive, roughly spherical dark matter halo that the entire galaxy is embedded within.
So the bar is rubbing against the dark matter, metaphorically speaking.
Sort of, yeah.
Yeah.
As the bar rotates through this sea of dark matter particles, its gravity pulls on those particles, creating a slight overdensity, like a wake, behind it in the halo. And the gravity of that wake then pulls back on the bar itself. It's effectively transferring angular momentum rotational energy from the spinning bar to the surrounding dark matter halo.
Okay, that makes sense. So the bar loses momentum and slows down. And what does a decelerating bar do to the stars in the galaxy? Does that have observable effects?
Oh, absolutely. It's crucial. As the bar slows down over billions of years, its resonances, remember quartation, the Lindblad resonances,
Hmm.
they don't stay fixed at one radius in the galaxy.
Oh, they move.
They slowly sweep outwards through the disk, through phase space, and as they sweep, they pull and drag stellar orbits along with them.
Right.
The sweeping action is thought to create multiple resonant features, these specific patterns in velocity space, that are now beautifully visible in the high-resolution kinematic maps we get from Gaia.
And here's the kicker, I bet.
And here's the kicker. This process, particularly the outward sweeping of the quartation resonance as the bar slows down, provides a remarkably precise dynamical explanation for the detailed kinematics we see in the Hercules stream.
No way. So the local stream is explained by the bar slowing down far away.
Exactly. It ties the deceleration of the distant bar directly to the specific pattern of stellar velocities we observe right here around the sun. It all fits together.
That is absolutely incredible. A specific feature near us is basically a fossil record of the bar slowing down due to interaction with invisible matter.
Very much, yeah.
Did they manage to quantify how much it's slowing down?
Yes, the studies were able to estimate the bar's current deceleration rate. It's roughly minus 4.5 kilometers per second per kiloparsec per billion years.
Okay, so it's a slow process, but measurable.
Measurable thanks to Gaia's precision, yes. It's the rate at which its pattern speed is currently decreasing.
And I remember reading they even used stellar chemistry, the metallicity of stars, to add another piece to this puzzle. How did that work?
Yeah, that was another really clever approach. They used Gaia's photometry, the precise measurements of stellar brightness and color, to estimate the metallicities of huge numbers of stars, basically how many heavy elements they contain. Researchers realized that if the bar's resonances are indeed sweeping through the disk as it slows down, they shouldn't just affect velocities. They should also subtly sort stars by their origin and therefore potentially by their metallicity.
Ah, because stars born further in or out might have different chemistry?
Exactly. So you might expect to see subtle variations in the average stellar metallicity depending on a star's location relative to the center of the moving resonance.
Okay.
By looking for this predicted metallicity variation among stars right here in the solar neighborhood and relating it to their velocities, they were able to derive a new, remarkably precise measurement for the bar's current pattern speed.
And what value did they get?
They got 35.5 plus or minus just zero point 0.8 kilometers per second per kiloparsec.
Wow, that's really precise. And does that super precise speed match up with explaining Hercules and the other features?
It lines up beautifully. That pattern speed puts the correlation resonance radius at around 6,600 light years, or 6.6 kiloparsecs. And that precise speed and the corresponding resonance location turns out to exactly match the detailed kinematics observed in the Hercules stream and other resonant features in the solar neighborhood velocity map from Gaia. It's a fantastic consistency check.
So, okay, let's pull this together. We have multiple lines of evidence now, all thanks to Gaia's precision. We have the overall kinematic map showing bar signatures. We have the direct connection to specific local streams like Hercules. And now we even have hints from stellar metallicity variations. And they all point towards a bar that is measurably slowing down. What's the ultimate significance of pinning down this deceleration?
Well, if you connect all these threads, the implication is pretty profound. It means the bar has likely lost a significant chunk of its initial angular momentum since it formed, maybe something like 20–25% over the last 8 billion years or so.
Okay.
And this lost angular momentum is being transferred to the dark matter halo through this process of dynamical friction. So the bar's deceleration isn't just some minor detail about its speed. It's actually providing tangible, albeit maybe circumstantial, but still powerful evidence for the existence and the dynamical influence of a standard cold dark matter halo surrounding our entire galaxy.
It's like using the bar as a probe for the dark matter.
Exactly. And it also poses a real challenge for alternative theories of gravity, things like MOND, that try to explain galaxy rotation without invoking dark matter. It's harder for those theories to naturally account for this kind of bar deceleration via dynamical friction.
That really is a profound conclusion, just derived from watching how stars move with incredible precision. It honestly feels like Gaia has just thrown open a whole new window into understanding how our galaxy works.
Absolutely. It really has transformed the field of galactic dynamics. And with every new data release from Gaia, we get an even clearer, sharper picture of the phase space of stars, their positions, and their velocities.
So more discoveries to come.
Oh, undoubtedly. We can expect many more insights in the coming years about the Milky Way's bar, its interaction with the spiral arms, its connection to the bulge, and its crucial role as this probe for the invisible matter that dominates the galaxy's total mass.
Okay, so to wrap up this deep dive then, we've explored what a galactic bar actually is, how incredibly common these structures are across the universe, but also the unique challenge of studying our own bar because we're stuck inside the dusty disk. We journeyed into the complex dance of stellar orbits and resonances that allow these bars to form and maintain themselves over billions of years.
Right. That orbital structure is key.
We saw how astronomers used really creative indirect methods for decades to get the first initial estimates for our bar's properties, its size, its mass, its orientation, and how they found hints that its dynamical influence subtly shapes the motions of stars far from the galactic center, even right out here near us.
And then, most dramatically, we've highlighted how this absolute wealth of data from the Gaia mission, especially when combined with other surveys like ATG, has just revolutionized our understanding.
Yeah.
It's not only revealing the bar's structure and its motion with totally unprecedented clarity, but it's providing this compelling evidence that the bar is actually slowing down over time.
Right, due to that dynamical friction with the dark matter halo.
Exactly. Essentially using this visible, yet still somewhat hidden structure as this incredibly powerful probe for the invisible matter that really holds our entire galaxy together.
It really underscores that understanding this crucial hidden bar is absolutely fundamental if we want to piece together the complete evolutionary story of our own Milky Way galaxy.
Definitely. And, this raises a really important thought for you, the listener, to consider. How incredible is it really that by precisely measuring the movements of stars right around us here in our local corner of the galaxy, scientists can actually deduce something profound about this massive structure? thousands upon thousands of light years away, deep in the galaxy's core, a structure we can't even properly see clearly.
Yeah.
And in doing that, in studying that bar's subtle influence, we find powerful evidence for the existence of the mysterious, invisible dark matter that seems to make up most of the matter in the entire universe. It's just a remarkable testament to the interconnectedness of everything in the cosmos, everything we see, and maybe even more importantly, everything we don't.